Today we're going to talk about simple harmonic motion. Before we get started, please take out your equation sheet since we'll be talking about a lot of equations for this unit. Before we get started talking about simple harmonic motion, we are going to review Hooke's law, which we briefly talked about in Unit 2 with forces. Take a moment to find this on your equation sheet. Let's go over this equation since we'll be using it pretty frequently in this unit. This first part is the force on a spring, and we measure that in newtons. And this X is our displacement, and that is in meters. Now this K here is our spring constant, and our spring constant is simply just rearranging this equation. So what does this look like? So our K equals negative Fs, so our force over X. So that means our units are newtons over meters. So it's really just a proportion. We're going to be using this when we talk about springs a little bit later on. All right, let's get to the new concepts. So this unit is focusing on simple harmonic motion, and we're going to start talking about frequency and period. When we talk about simple harmonic motion, we're simply just talking about a motion that repeats itself over and over again in a uniform pattern. So in some ways, this is similar to uniform circular motion or gravitation, which you learned earlier this year. First, we have our period, which is big T, and this is the time it takes to complete one cycle. So if we're thinking about a pendulum, it has to go back and forth to do one period, big T, and this is in seconds. Frequency is the number of oscillations per unit of time, simply the inverse of T. So what are our equations for this? Take a moment to find this on your equation sheet. You'll see period equals 2 pi over little omega, we'll talk about that in a minute, equals 1 over f. So pretty simply, our frequency and period are just inverses of each other. And what's this part of the equation? Well, this is another way to find period if we know what this little omega is, which is angular velocity. Now, we don't learn about this till next unit, so don't worry about this right now. You'll see a little bit more how that ties in there. One of the most common ways to represent our simple harmonic motion is through graphs, and this is very common in the AP Physics test, especially because we don't learn about waves anymore. So this graph may look a little complicated, but it's actually pretty easy to understand. So on the left side, you'll see I have a really great drawing of a spring. So let's say I have my start, which is right here at equilibrium. And then I stretch my spring with a displacement, which we call A, and that's our amplitude. So we can think about displacement as amplitude in these situations. So that's where I reach right here. So it's going to move, and then it's going to start coming back. So eventually it's going to go right back through that equilibrium, which we see at that point. Now this is not a full period. This is a half a period at this point, because it has to go back to its original point. So then we're going to see a compression. So here we have negative A, and then it goes back to its original spot. And then we finally have a full period. Now there is an equation to go along with this. Take a minute to find this on your equation sheet. So this is the period of a spring equals 2 pi square root of m over k, mass and spring constant. And this is our mathematical way to find the period of a spring if we don't have a graph. In the previous slide, I talked a little bit about how we determine our amplitude, but we can also apply this to energy. So if we think about this, when the spring is going through this center part, so right here and right here and all the way across. So this is where I have my max velocity. So therefore, I have my max KE. We use the same equation we have used before. Take a minute and find that on our equation sheet, 1/2 mv squared. Now when it is at these other points, so we have minimum and maximum amplitude or displacement, whichever way you want to think about it. This is when I have no velocity and max potential energy, aka big U. Now, what is my equation for I use for this? It's a little bit different. You can find it on your equation sheet. So this is potential energy of a spring equals 1/2 kx squared. So we can actually use these to determine the energy at different places as we go across. We'll do this a little bit more in class. Now we also have an equation to represent how to find the displacement. So when I talk about displacement, we mean over a period of time, how far did it travel? So for instance, from here to here, how far did it actually go up and down? Take a minute to find this on your equation sheet. Now this isn't really commonly used, but it is good to explore it. So right here, amplitude is how much it is going up or down. This is a constant number, cosine 2 pi. F is frequency, and then T is our time. Now, how does this work out with our units? Frequency is 1/seconds, and time is S. The last concept we're going to review is simple harmonic motion in a pendulum. Pendulum is simply just a bob moving back and forth over time. As a reminder, a period, it needs to go through the center and all the way back to its starting point. Take a moment to find the period equation for a pendulum on your equation sheet. It looks very similar to the equation for a period for a spring. The only difference is in the square root. So this is the length of the pendulum and the gravity. Now what we'll be doing in class is working on an experiment where we are proving this equation and also discussing how energy plays into this.